able to capture my screen for this lecture called Screencastify, and I'm having some technical difficulties. But this should be part one of a larger lecture about electric current and DC circuits. Chapter 18 covers electric currents and 19 DC circuits in your textbook. We are cutting and pasting, though. We only need to worry about sections 1 through 5 of Chapter 18. Our focus is pretty narrow here for the last bit of AP Physics. So Alessandro Volta is given the credit for the discovery that current could be created if dissimilar metals were connected by a conductive solution called an electrolyte. Alessandro Volta is given credit for developing the first battery type device. This kind of situation of two types of metals, one that tends to give off electrons, another that tends to accept electrons, connected together through a conductive medium, conductive solution, such as an acid, is a simple electric cell, as in a simple battery. So the idea is that a battery transforms chemical energy into electrical potential energy. We've looked at electric force between charged particles, and just like gravitational force between two objects causes or is the source of gravitational potential energy, the electric force between two charged particles causes, in a very similar way, an electrical potential energy. And you can think of a positive charge and a negative charge that you hold away from each other, and how that attractive force would cause those two charges, if you let them go, to accelerate towards each other. And that acceleration can be expressed as a gain in kinetic energy. We talked about a similar situation with holding a bowling ball above the surface of the earth, where letting the bowling ball go would cause the bowling ball to gain kinetic energy. And we talked about that gain in kinetic energy is coming from a transformation of gravitational potential energy to kinetic energy. We have an identical situation for charged particles. So a battery is serving to transform chemical energy, so the chemical energy held in that configuration of dissimilar metals and acid solution, into electrical potential energy. Chemical reactions within the cell create a potential difference. And so our focus in circuits is not actually on electric potential energy per se, but the electric potential energy available per charge in the system. So we call that electric potential energy per charge electric potential. The potential difference then is a difference in electric potential energy per charge available to move, and the potential difference is due to the dissolution of the terminals. The potential difference can be maintained even if a current is kept flowing until one or the other terminal is completely dissolved. So if the chemical reaction has been spent, there's no longer chemical potential energy available to transform into electrical potential energy, and the battery, we say, is dead. So electric potential and potential difference are both measured in volts. Well, electric potential and potential difference are the same thing, essentially. And we measure in volts. We also call it voltage. Electric potential difference is called voltage. So this is a bit of a vocabulary problem. Voltage is measured in volts with the symbol capital VE, both for voltage and for volts. It's fun. So several cells can be connected together to make a battery. However, we also refer to a single cell as a battery as well. We're really not concerned with the nomenclature here. We're just going to consider batteries to be sources of electric potential. So electric current is defined as the rate of flow of charge through a cross-section of conductor. So current is given the symbol capital I, and current is defined as delta Q divided by delta T. How much charge, delta Q, passes a cross-section of conductor in a particular delta T. The unit of current is the ampere. So the symbol for ampere is capital A. So I is our symbol for current. A is our symbol for the unit of current, ampere. And 1 ampere is 1 coulomb per second. We've discussed this the largeness of the unit of a coulomb. So 1 coulomb is a very large amount of charge in everyday situations. So 1 coulomb per second is also a very large amount of current. You might refer to like the circuit breakers in a circuit in your house. The circuit breaker will break at currents exceeding 15 amps usually. So just 15 amps is rather a lot of current. In class, we will look at light bulbs, batteries, and wires, and we'll investigate connections of light bulbs, batteries, and wires, and ways to make complete circuits, and then compare them. We'll come back to this activity. For now, I just want you to get the basic ideas. So a complete circuit occurs when current can flow all the way around. An actual circuit of components does not necessarily look like a schematic drawing. Right? The physical circuit doesn't always look like the drawing, but we'll use schematic drawings to simplify and to give directions, clearer directions for constructing circuits. So on the left here is an actual circuit of battery, wires, and light bulb, and on the right is the schematic of the same circuit. In order for current to flow, there must be a complete path from one terminal of the battery to the other. Circuit has to be able to flow all the way around through battery, through conductors, and through any elements you're connecting. Only one of these circuits works, and that's kind of the focus of our in-class demonstration. By convention, current is defined as flowing from positive to negative terminals of a battery. The electrons are actually flowing in the opposite direction. Electrons are negative, and so they flow from the negative terminal of the battery to the positive. This is just a holdover from like Benjamin Franklin era and confusion about what particles were actually charged and what particles were actually moving in current. So conventional current is the flow or sort of the imagined flow of positive charge. It really doesn't matter because they're exactly opposite to each other. The only time it matters is if we're concerned with something like a diode, a one-way device, and we will not consider diodes in this course. So Ohm's law relates resistance and resistors to voltage, which is potential difference, so the push through the circuit, and the amount of current that's allowed to flow. So typically Ohm's law is expressed as V equals IR. But I also like to think of Ohm's law as current, I, equals V divided by R, because that orientation of Ohm's law shows Ohm's law as almost a Newton's second law idea, where the current, the movement of the charge, is equal to voltage, the push on the charge, divided by resistance, the resistance of the charge to moving through a particular element of the circuit. In many conductors, resistance is independent of voltage, and when that's the case, the resistor or the conductor is called ohmic. That means that Ohm's law is followed. But there are also materials that do not follow Ohm's law, and they are non-ohmic. We will not consider non-ohmic materials. The unit of resistance is the ohm. 1 ohm, so given by the symbol omega, capital Omega, and 1 ohm is defined as 1 volt per amp. So clarifications, batteries maintain a nearly constant potential difference, even if the current varies. And battery, at least ideal batteries, and we will only consider ideal batteries who maintain a constant potential. Resistance is a property of a material or device. It has to do with area and length and the type of material. It has to do with how many valence electrons are available. Current is not a vector, but it does have a direction. So it's not a vector, but we do sometimes concern ourselves with direction of current, especially if we're working with something like a diode. Current and charge do not get used up. That would be a sort of measurement of energy, and we know that charge is conserved. So whatever charge goes in one end of a circuit comes out the other end. And it looks like I'm approaching my recording limit, so I'll pause here and restart on the next slide.